Okay, so let's get started. So remember so at the end, last time I was saying something about like bow ties and this sort of thing. Did you guys understand? Did that make any sense? Sort of. Let me see if I can sketch it out a little bit better. So like, right, so differentiable at a point x naught. So f differentiable at a point x naught. Remember, what that means is that f means that f minus the linearization at x naught equaled u of x minus x naught for some function u such that as x approaches x naught, that thing went to 0. Right? That's what we said. Right? That was our alternate view of the derivative. Right? Right. So in particular, right, u goes to 0. So given any, maybe I'll use the letter m. Okay. Given any slope m, positive slope, and again, let me put absolute values on this guy. Given any slope m, there exists a neighborhood around x naught in which the absolute value of u is smaller than m. Okay, so there's some delta neighborhood around x naught in which the absolute value of x is smaller than m. In other words, if we look at this thing, f of x minus L of x, well, that's going to be smaller than m x minus x naught. Right? Because f minus L equals u times x minus x naught. Right? This thing is smaller than, well, it's equal to absolute value of u times x minus x naught. Right? And this thing is smaller than m there. Right? Strictly smaller. It doesn't matter. Okay, so, what does that mean? That means that this thing here is trapped between the positive guy and the negative guy. Right? Right. That's what absolute value means, right? Okay, everybody all right? Everybody following? Okay, so what does that mean? That means that, so here's your function f, and here's the tangent line L, right? And so it says, whatever m you choose, and m is a slope, right? Whatever m you choose, whatever slope you choose to add on to the slope of this guy, right? Whatever slope you choose to add on to, maybe I should write it like this, it doesn't matter. Let me write it like this. Whatever slope you choose to add on to that of L, there's a neighborhood of x naught in which your function, so there's a neighborhood of x naught, right? In which your function stays within those bounds. So, right, whatever bow tie or butterfly or whatever you want to call this thing, whatever bow tie you choose, right, no matter how small an aperture, right, whatever bow tie you choose around this tangent line, there's a neighborhood in which your function stays on the bow tie, on the wings. Okay, and that's what differentiability. That's what differentiability means. Okay, it's just I'm just sort of recasting it again. Okay, and you see that this goes well with the line-like interpretation, right? I can choose a very thin aperture here, very narrow aperture here, and I'm guaranteed a neighborhood in which my function stays on that thin bow tie. Okay, so I can make it as line-like as I desire. Okay. Okay, I hope it's clearer now than it was at the end. Okay, so now let's use that to, now so today we're going to prove like all the results, well, maybe not all, but most of the results in differential calculus. And you'll see that they're all basically the same result. Okay. They're all basically sort of like incarnations of the mean value theorem. Okay. So first, except for this one. Except for this one. This is the one that's different. Critical point theorem. Okay, so let me make sure I get it written down right. So you have a function on a closed and bounded interval. If f has a local max or local min at some x naught in AB, and B, the derivative exists there, then the derivative must be 0. Okay, so of course, if f has a local max or min somewhere, right, at some point x naught, then either the derivative is 0 or the derivative doesn't exist. Right? In other words, x naught is a critical point. Okay, so I'm sure you've seen this thing before in calculus. Okay, and the proof is pretty straightforward, right? You just say, well, look, if the derivative is, for example, greater than 0, right? So then you'd have this sort of picture, right? That here's your point. The linearization with positive slope, right? Then if the derivative is positive, then choose an aperture. Choose an aperture for your cone that is smaller than this, right? Right is the proof, is the idea at least. choose m that's smaller than f prime. Right? What does that mean? That means that the slope of the lower edge of the cone here is positive, is still positive, right? Because I'm going to take that slope and I'm going to subtract, the slope of this thing is f prime x naught minus m, right? Right. The slope of this guy is f prime x naught minus m. The slope of this guy is f prime x naught plus m. Right. I don't care about that guy, just the lower guy, right? The slope of the lower guy is positive, right? And I know that, by differentiability, I know that there's some interval, right? There's some neighborhood in which my function stays within these bars, right? Stays on the wings, right? If my function stays on the wings here, then the points on the right side have to be bigger than the point here. That's the end, right? So it cannot be, right? Thus, f x naught cannot be a max. Contradiction. Okay, that's basically the proof. Okay, so if we're trying to show that the slope is 0, suppose it's bigger than 0. Choose m smaller than m prime. We know that, by the definition of differentiability, we know that there's this cone on which the function stays within stays on the wings, right? And so it's got to be rising there. It's got to have higher values there. It has higher values there, and so cannot be a max. And then similarly for if f prime is less than 0, we do something similar. Yeah, we would just use the left. We would use the left side rather than the right side. Okay. Do people want me to write that out more formally? I can write it out. Actually, let me write it out more formally, just for just to make sure everybody's all right. So, without loss of generality, assume that f prime is positive. Right? If it's negative, we can do exactly the same argument. Okay. So have I used this before without loss of generality? Yeah. Okay. Great. Okay. Okay. So yeah, choose an m such that m is smaller than f prime x naught. Right? By definition of differentiability. By definition of differentiability, we know that f is trapped between the linearization plus m times x minus x naught and the linearization minus m times x minus x naught. Okay, so now on the right half interval, right, on x naught comma x naught plus delta, right, so because of differentiability, there exists a neighborhood of x naught in which this holds. Right. Now look on the right. Now look on the right half of that, right? And let's just use the left inequality, right? We get f of x naught plus f prime x naught x minus x naught minus m x minus x naught is less than f. Right. The line, remember, this is the linearization. Minus this guy, x is now bigger than x naught, so I can throw out the absolute value sign. Right? But that says, using the distributive property, that's the same thing as saying this, right? Of course, right? And this is positive, right? This thing is positive, right? The slope of the lower edge, right? The slope of the lower edge was chosen to be positive, right? So we get this positive number times this positive number, right? So f of x naught plus some positive number is still smaller than f of x, right? For any point on the right side here, f of x naught plus some number, plus some positive number is still smaller than f of x, right? So f of x is bigger than, right? F of x is bigger than f of x naught. So f of x naught could not have been the max. Yeah, Rishi.
So since we're talking about like a local extremum, would we technically have to like intersect the neighborhood we get from differentiability with like whatever neighborhood in which x naught is?
Yeah, okay. So yeah, I would say like can assume, assume the delta is small enough.
Yeah.
Thank you. That this thing is contained inside of the integral a b, say. But we can do that, right? Because, you're always allowed to shrink your delta. If you find one delta that works, then any delta smaller than that is still going to work. But good catch. Okay. Okay, good. People all right? Okay. So, right, intuition, translation. Okay. Like formal version, and what's actually happening under the formal version. But they're the same thing, of course. Okay. So. Okay. Okay. So now we're going to prove a long string of results using the critical point theorem, which is said to be due to Fermat. No, I shouldn't say that. Which is due to Fermat. He of Fermat's last theorem fame, plus the extreme value theorem. Right. That we had to get using the ideas of compactness, right? So remember, of course, that f of AB, if it's continuous, then f attains a max and a min on AB. Okay. Okay. From these two theorems, everything is going to spring forth. Okay. So. First off, let's go for the so-called Rolle's theorem. Anybody remember the statement of Rolle's theorem? You are shaking. Why?
If f is defined on some interval AP, if fa equals fb, then there's some point on which the derivative of f is 0.
Exactly. Right. So you've got some function on a closed and bounded interval. You have that f is continuous on the closure. You have f is differentiable on the interior. And you have that f of a equals f of b. So if all those three things happen, then there exists a point C between a and b where the derivative is 0. physically speaking, it says that if you have a car that starts at one point on a track, right, and then it ends up at the same point on the track, then it must have had velocity 0 at some point in between, right? So it's like it had to turn around and have velocity 0 at some point. Okay. So yeah, so that makes it sound really, really like unimpressive, right? But I should say that there are kind of really pathological things in mathematics, like the so-called Cantor-Ternary function, which is differentiable. It's continuous on AB. It's differentiable almost everywhere. On the interior. And you can think of this almost everywhere as being sort of like 100% of the time. So barring a set of points that has zero measure is what it technically means. Okay. In any case, the Cantor-Ternary function is differentiable almost anywhere and has derivative 0 when differentiable. But f of 0 is 0 and f of 1 is 1. Okay, so you can have some sort of strange constructions that are differentiable basically 100% of the time, and they're continuous, but they still move. Okay, just to make it things a little bit more interesting. Okay. Okay, so proof of Rolle's theorem. Yeah, do you guys want to? I'll let you try it. But see if you can prove Rolle's theorem. The key points are, as we said, the extreme value theorem and the critical point theorem. You can probably do it. Just put the pieces together. You have all the parts. Okay, anybody come up with a proof or some idea? Like what's the first move to make? Which one should we use? Extreme value theorem or critical point theorem? Votes. This one? This is the right one. Right? So by the extreme value theorem, right, we know that there exists a max and a min in AB. Right, there's some point in AB where we reach a max, and some point in AB where we reach a min. Okay, and if one of them is inside here, right? If one of them is in the interior, then we're done. Right? Because if one of them's in the interior, by the critical point theorem, we know that because it's differentiable there, the derivative must be 0. That's the end. right? So case, if one is in AB, then by the critical point theorem, we're done. Right? Because we know that then the derivative at whatever point that is going to be 0. Okay. What's the other case? What's the other case? First case is one of the points is in AB. What's the other case? Rishi?
Both of the extrema are the endpoints.
That's right. Neither of the points are in the interior, right? So neither is in AB. In other words, both are at the endpoints. Okay. But in that case, the maximum and the minimum are the same value, right? But then the max equals the min, and the function is constant. Right, the function is constant. So it definitely has points where the derivative is 0. Okay, good. Oh, hold on. People are still writing. Okay, so Rolle's theorem. From Rolle's theorem, we get to the important mean value theorem. Okay, right. So what's the mean value theorem saying? Anybody remember or have a picture in their minds? Rishi, go ahead.
If our function is like continuous and differentiable out of a closed interval, then there's some point where the derivative is the like mean value, or if like f of b minus f of a all over b minus a.
So same sort of setup, right? You got f continuous on AB, f is differentiable on the interior, but that's it. Now we don't have the boundary conditions, okay? But even so, still, there exists a point in the interior where f prime equals f of b minus f of a over b minus a. Okay, right? The usual picture looks something like this. And you have some point A, some point B, right? Right, the f of b minus f of a over b minus a is the slope of the secant line, right, through these endpoints. And what it's saying is that there's some point in the interior where the slope of the tangent line equals the slope of the secant line through the endpoints, right? That's the geometric version, or if you like the physical version, there's a point where the instantaneous velocity equals the average velocity over that time, over a time interval, right? You're thinking of this as position over time. Okay. Okay, and the proof of this is basically to sort of like use Rolle's theorem anyway. Okay, so like the Rolle's theorem doesn't apply, right? Rolle's theorem doesn't apply because we have this we have this function and f of b does not equal f of a. Okay. But what we do is we say, okay, let's just make it apply, Okay, so what we do is we take another function, here's f, we take another function, L, which is just the secant line through those points. Okay, and then consider the function d defined as f minus L. Right. So what is d of a? 0. What is d of b? 0. Right. Further, d is continuous on differentiable on the interior, and continuous on the closure, right? Because each of the pieces are period. Right. And so we can apply Rolle's theorem to it, right? So apply Rolle's theorem. And we get, there exists a point in AB where the derivative of d is equal to 0. Okay. What does that tell us about? Tell us about f. Now we translate that back into information about the thing we really cared about, which was f. Right? Remember, d is f minus L, right? So we know that f prime of c minus L prime of c is equal to 0.
F prime c equals L prime c.
F prime c equals L prime c, right? And what's L prime c?
The sum of the secant line.
Exactly. Okay. Okay, so we're kind of in the situation where we have a function, the theorem doesn't apply to it, but if we sort of toggle, if we sort of tweak the function in a delicate way, if we tweak it delicately, we can create something to which the theorems, the old theorem still applies, and then use that result of the old theorem to the tweaked guy to get information about the actual guy. Okay, so that's the strategy. Like, apply the theorem anyway. Okay. Yeah, and notice that, no. Yes. Yeah, notice that, of course, Rolle's theorem falls out of the mean value theorem. If you have the mean value theorem, right, then f of b equals f of a, and you've found a point where f prime equals 0. Okay. Yeah. Okay. So now notice something that I could have at this point. All I needed here was to create a function that I didn't have to use this function, this L, right? I could have used, for example, like L shifted by some, by some constant or something like that, right? Because as long as the values are the same, as long as the values, right? As long as the difference has equal values at the endpoints, then I can still apply Rolle's theorem, right? Okay. But actually, there's a little bit more leeway in this than that. Like, I could take basically any function, right? I could take any other function, right? And look at the difference, and I can apply Rolle's theorem to that, right? Because as long as the difference at the endpoints is the same, Rolle's theorem can apply, right? So let's do that. Let's create like a Rolle's theorem number 2. Okay, So given two functions f and g that are, as usual, continuous on AB and differentiable on the interior. Okay. Such that f of a minus g of a equals f of b minus g of b. Then what? Write down what Rolle's theorem would say in this case. Right. Basically just imitating what we just did to get the mean value theorem. Turn to a neighbor and say, this is what happens. No. That's not what I meant.
Yes.
Yeah. Yeah, because also like it's the same thing if you treat like this f of n as like f, actually as like
What do we figure out?
Okay.
Right, that's what we did.
So what happens, right? What happens? What happens? Harrison?
There's a point C in the open interval AB where f prime C equals g prime C.
Exactly, right? So instead of getting, the slope of the line, we'll get, the slope at that, the slope of the tangent line to the other guy, right? So there exists a point in AB where the instantaneous velocities are the same. Right? Proof, look at the difference. Apply Rolle's theorem to the difference. Okay. Right. There's going to be a point where the derivative of that guy is 0. In other words, where f prime equals g prime. Okay. Okay. Now we're going to go for this thing called the generalized mean value theorem. And so the thing is here. So right now, so we started off with something like this, right? We moved on to something like this. Then we moved on to something like this, right? And now we're going. So this was, Rolle's. This is mean value theorem. This is Rolle's 2. Rolle's. So then now we're going to do something like this. Okay. So that is we put on no constraints. Okay. No constraints. So almost no constraints. This is called the generalized mean value theorem of Cauchy. So you have two functions, f and g. And as usual, with a continuous closure and differentiable on the interior. And that's it. Okay. Then something happens. So how should I present this? Okay, so think like this. This is probably not the way to do it, but let me. No, let me do it the right way, sorry. Sorry. My natural tendency towards teaching is to present it like it's a big mystery, and like then you sort of like work through it, and then bang, the result comes out. But pedagogically, that never works. I've been teaching for, I don't know how many years now, 30 plus years now, and that never works. So I'm going to tell you the result, and then we're going to prove it. Okay.
Mystery is more fun.
I know mystery. It sounds like it's more fun, right? You would think that that's the better way to do it, but it's not really. Okay, so then there exists a point in AB where f prime c times g of b minus g of a equals g prime c times f of b minus f of a. Okay, let me just make one remark. If we knew that, assuming that if we also impose the condition that g prime is never 0, then we could say we'd have rather f prime c over g prime c equals g of b minus g of a, sorry, f of b minus f of a over g of b minus g of a. Okay, so I generally like to do it that way because it looks nicer. Okay, and second remark, this is actually the remark I want to make. Notice that I can think of this as, this thing here is the ratio of the instantaneous velocities, right? And this thing here is the ratio of the average velocities, right? Because I can put in this, I can divide top and bottom by b minus a. Right? And so I've got the average velocity on the top and the average velocity on the bottom, right? So it says that, here what we were saying is that if you have two cars and they start at the same distance apart and they end at the same distance apart, there must be some point where they are traveling exactly the same velocity. And this is saying that if you have any old pair of cars, then you know that there's some, as long as they start and end at the same times, it doesn't matter what they do, you know that there's some point where the ratio of the instantaneous velocities equals the ratio of the average velocities. Okay, so that's pretty cool. This result is due to Cauchy. Whose name you'll see a lot later. Cauchy is sort of like the great complex analyst. Like everything in complex analysis is due to Cauchy. The Cauchy integral formula, Cauchy Riemann equations, Cauchy, everything's due to Cauchy. Cauchy inequalities. Okay. Okay, so the proof is, right, we've got these two functions, f and maybe g. Okay, and so we want, the strategy is again to try to tweak G, say, so that we can apply Rolle's number 2. Okay, what were the conditions of Rolle's number 2? Remember, Rolle's number 2 had to be where that, you know, the difference between the endpoints was the same. Right? Something's wrong here. That should be B. Right? Or equivalently, the change for each function was the same. Okay. Okay, so what we do is we say, let's multiply g by some constant, alpha, so that we can apply Rolle's to the pair f alpha g. Okay, so what's alpha? What's the alpha we want? Go ahead, Rishi, go.
I'm not sure if this is right, but is it just like g of b minus g of a divided by f of b minus f of a?
The other way around.
Or,
Yes,
yeah.
yes. Right, because you want this. Oops. You want this to be this, right? So what's alpha? Well, just divide by g. Just solve for alpha. Right? So let alpha be f of b minus f of a over g of b minus g of a. And notice that we know g of b minus cannot equal g of a since g prime is non-zero. Right? If g of b equal g of a, Rolle's theorem would tell you there's a place where it's 0. But we impose this extra condition that g prime is never 0. Just so that we could divide by this. That's the only reason. Okay. So now apply Rolle's 2. That says that there exists a point C where f prime of C equals a g prime of C. Right? Rolle's 2 said there's a point where the instantaneous velocities are equal. Right? So there's a point where the instantaneous velocities are equal. In other words, f prime of c over g prime of c equals alpha, but alpha was the ratio of the differences. Yeah,
if we were trying to also handle the case where the endpoints are equal, would we just like use the point where g prime is 0, guaranteed by normal rules, and then
it's simpler than that. You would rather just multiply f by this constant and multiply g by this constant.
oh yeah, that makes sense.
Yeah. right? And then you would get a point where, you would get a point where g of b minus g of a times f prime c
Yeah.
equals f of b minus f of a times g prime c, which is exactly what's in there. Yeah. Okay, are you guys okay? Seem kind of tired. Okay, what I'm going to show you now will only make you more tired. I don't even know if I want to do this, but I'm just going to write up the results because you've seen this before, I'm sure. Corollaries of the mean value theorem. So this is not, I could have done this after the mean value theorem, but corollaries of the mean value theorem. So if you have f continuous on AB and differentiable on the interior, then you guys know this, right? If f prime is bigger than 0 on AB, then the function is increasing, right? If it's less than 0 on AB, then it's decreasing. And if it's equal to 0, then it's constant. Okay. It's not the most interesting thing. Let me just put up the proof of one of these things. I don't know, let's do the first one, say. Proof of 1, right? So you've got this interval, and you know that the derivative is positive here, right? So if I take any 2 points, x1 and x2, then I know that, by the mean value theorem, I know that the slope of the secant line is something positive, and so this point must be higher than this point. That's the proof. Okay, so let me write it out. Choose x1 and x2 such that they're in the interval and x1 is to the right of x2. Then f of x2 minus f of x1 over x2 minus x1 is some positive number. Right? But then f of x2 minus f of x1, right, this denominator is positive. Right? x2 minus x1 is positive, so the numerator must also be positive, and so the one on the right is bigger. Okay, so that's, the rest can be proved in the same way. Okay, let's go on to something more interesting. So L'Hopital's rule, from the generalized mean value theorem, we can get L'Hopital's rule. So let me write it up properly. Okay. So I'm going to put it up in the full generality that Rudin says, but I'm going to just prove it in one case. But I think it's useful to see the full-blown version. So suppose f and g are differentiable on some interval, some open interval AB, and it could be an infinite interval. Okay. Suppose that G prime is never 0 there, and that and the limit as x approaches a of the ratio of the derivatives is some constant. Okay, and the constant could be, again, in the full-blown version, the constant could be infinite. Then, if the limit of f as x approaches a equals 0, and the limit of g as x approaches a also equals 0, then now we have our usual conclusion. Then the limit of f of x over g of x equals the limit of the derivatives, the quotient of the derivatives. Okay, so this is the sort of full-blown version of L'Hopital's rule. Okay, but I'm only going to do it. So we'll do the case of where A and capital A are finite. Okay, so here we go. Give me a second. I want to make sure I know what I'm doing. Yeah. Okay, so let's call this thing A. Right. We want to show that there's some neighborhood of A in which, so we want to show that, as usual, given epsilon greater than 0, there exists a neighborhood of A in which f of x over g of x minus a is smaller than epsilon. Right? That's the usual goal. Okay. So now we know that the limit of the ratios of the derivatives is a. Right? So we know that there exists a neighborhood n delta a in which f prime x over g prime x minus a is smaller than epsilon over 2, say. Okay, so now take any interval x, y inside a plus delta. Okay, so choose your delta so that the delta neighborhood lies inside of the AB interval. Okay, so then the generalized mean value theorem says that there's going to be a point C in xy such that f of y actually, let me read it this way. F of x minus f. It doesn't matter. F of x minus f of y over g of x minus g of y equals f prime c over g prime c. Okay. Right? But this thing we know is within epsilon over 2 of A. Right? Because we're within the delta neighborhood. Right? The delta neighborhood was chosen so that this thing was close to the ratio of the derivatives was close to A. So here we've got a ratio of derivatives. It's close to A. Okay, and then not really sure. Yeah, okay, that's fine. That's fine. So now let y approach A. Okay. Let y approach A. Remember that we had that the limit of f of x as x approaches A and the limit of g of x as x approaches A are 0. Right? And so these guys vanish, right? And we get f of x over g of x minus this thing. Well, no. We get that this thing equals this number, which is within epsilon over 2 of A. Okay. So that tells us that for any x inside here, we have for any x inside the delta neighborhood, f of x over g of x is within epsilon of A. And that's what we wanted to show. Yeah, Rishi.
Did we need epsilon over 2, or could we have just used epsilon?
Well, the thing is that this is kind of, in some sense, no, and in some sense, yes. The reason you need it is because we're trying to show that this thing is within the thing is that the c changes with the y, right? The c changes with the y. So this thing is within epsilon over 2 of A, but when you take the limit, the limit could be like, instead of being less than epsilon, it might end up being less than or equal to epsilon.
Okay, sure.
And so in order for me to say that this is satisfied, I don't want this to happen. So I chose the epsilon over 2 is taken so that you know that this is less than or equal to epsilon over 2, which is certainly less than epsilon.
Sure.
Yeah, that's why.
If our c is changing with the y,
Yeah.
what c do we, or how do we know that we end up on a well-defined c as y goes to A?
You don't, right? But you know that.
But is it just equal to any of them?
Sorry, maybe let me say this. Sorry, you're right. This is not right. What I should say is that the limit of this thing minus A is smaller than epsilon over 2,
sure.
less than or equal to epsilon over 2. Thank you. Yeah, no, that was imprecise. the next arc, yeah, so we have this first arc, right, that goes like Rolle's theorem to mean value theorem, Rolle's theorem to Rolle's theorem 2, Rolle's theorem 2 to generalized mean value theorem, right? Generalized mean value theorem to what he calls Rolle. Okay. And so now what we're going to do is basically take the whole thing and ask, what about nth order derivatives? Okay. And so we'll have basically something like an iterated Rolle's theorem. Iterated Rolle's theorem will give an iterated Rolle's theorem 2. Iterated Rolle's theorem 2 will give us the Lagrange form of the remainder for Taylor polynomials. Okay, and so it's basically the same sort of arc, but for higher order derivatives. Okay, so yeah, should I start it or? Yeah, I think let's stop there. I think doesn't make sense to start the next arc at this point. So we'll do that next time.